Okay, if you would take a look there, there is a starter question on there. First starter question is, what does absolute value mean? And the second question is, find the product of those two. Now, we've gone over imaginary numbers, haven't we, in this class? So if we were to multiply those together, I got all the 16. Can anybody tell me what absolute value means? The distance from zero, okay? So absolute value is distance from zero. Distance from our center point on our number line, or in this case, we're going to start talking about the distance that is from the origin, okay? And if we were to find the product of the two of these, we're multiplying two complex numbers together. Again, this is the real part, and that's the imaginary part. So if I multiply those together, it's kind of like multiplying polynomials. So I get negative 6, I get plus 15i, I get plus 8i, and then I get, let's see, that's a minus 20i squared. Okay? Now, what does I squared count as? A negative 1. So what's negative 20i squared count as? That's going to count as a positive 20. So when I multiply these together, I end up with a couple of like terms here. So that's going to be 14 for the real part. And what's the imaginary part? 23. So 23i. Okay? So when I multiply those together, I get a new complex number, 14 plus 23i. All right? Now, what we're going to talk about in section 6.5 is trig form of a complex number. So we're going to learn a whole bunch of funky things that you can do with complex numbers, but we're going to kind of blend, pardon me, what we've been talking about in terms of vectors and directions and lengths and all that sort of stuff. And we can find that there's something really cool that you can do, or an analogous type of approach that you can do with complex numbers. So some pretty awesome stuff. So a lot of times it's really helpful to draw a picture of what we're talking about. But the problem with complex numbers is you can't graph them on an XY plane, okay? But you can graph them on something that we call the complex plane. So if we're going to graph on a complex plane, what it will allow us to do is it will allow us to see some patterns and some things that we wouldn't be able to see otherwise, okay? So here's a picture of a complex plane. It looks very similar to an X and Y axis, except for instead of an X axis, we call this the real axis. And instead of a y-axis, we call this the imaginary axis. So we can take any complex number and think of it as if it were an ordered pair. So think of it as if it were an x and a y. So if I have the number a plus bi, remember this is called standard form of a complex number. Standard form of a complex number. We could think of that as a comma b. Think of it as a comma b. Remember, A is the real part and B is the imaginary part. So when I'm looking at a number like this, if I'm looking at 14 plus 23i, if I say what's the real part, you should say 14. If I say what's the imaginary part, you just say positive 23. You don't need to say 23i because we already know it's imaginary. We just stated it was imaginary. Okay? So there are lots of times where we use the letter Z to represent a complex number. So I've got 4 different complex numbers here, and we're just going to go ahead and graph them. So I'm going to graph Z1. Z1 is negative 2 minus 3i. So I graph that here. Negative 2 is the real part. Negative 3 is the imaginary part. So that's where Z1 is. If I want to graph Z2, negative 5 plus i. So back 5 and up 1, that would be Z2. Z3 is 4 minus 4i. So 4 is the real part, negative 4 is the imaginary part. So go over 4 and down 4. So that's going to be Z3. And then the last one that I've got right here is radical 3 plus I. And understood to be right there is a 1. So that means I go over radical 3. Now roughly what is radical 3? About 1.7. So I'd go about right here. and then I'd go up 1. So Z4 is right there. So now I've graphed those imaginary numbers, or those complex numbers, on the complex plane. Okay, so let's talk about something else. Okay, we can talk about the absolute value of a complex number, or the word that we a lot of times use for that, it's called the modulus. Okay, modulus and absolute value of a complex number are the same thing, and you'll notice that we use the same type of notation that we normally do. I put that in absolute value. Okay, so let's say I wanted to know the absolute value of this number right here, this complex number right here. I'd want to know how far it is from 0. So I'd want to know the straight line distance from 0 to there. Well, if the horizontal part, if the real part was radical 3, and the vertical part, the imaginary part, was 1, how could I use these two numbers to find that length right there? What is it? The Pythagorean Theorem. Yeah, I'd take radical 3 and I'd square it. I'd take 1 and I'd square it, and then I'd take the square root, right? Wouldn't that give me the hypotenuse here? Or the radius, or the modulus, or whatever you want to call it? Okay, so in this case we get 3 plus 1, radical 4, so we end up with a modulus of 2. The absolute value, or the modulus, for that particular number is 2. But in general, here's how we'd write it down. If it's in standard form a plus bi, then the modulus, the absolute value, is going to be a squared plus b squared underneath the square root. Okay? So if we want to find the modulus of this number right here, it means we're finding the absolute value of that. So it's pretty darn easy. We take the negative 3 and we square it. We take the negative 2 and we square it. And what do we end up with? Square root of 13, wouldn't it be? 9 here, 4 here, square root of 13. So if I'm at negative 3, negative 2, so I'm at this one right here, that distance right there is radical 13. Same thing on this one. Radical 3 over here, up 1 here. That distance right there, we just found it up there, that distance right there would be 2, because we're going to take the square root of radical 3 squared, 1 squared. That's going to be 3 plus 1. That's going to be the square root of 4, so that's going to be 2. Any questions? See some similarities when we're working with vectors in component form? Okay. All right. So just a reminder, when you started learning about logarithms, okay, maybe that was this year, maybe that was before, but when we start talking about logarithms, it seems like logarithms just make things really complicated. And what we're going to do here in a second is going to seem like we're making things more complicated. But the cool part about it is, if we make the original numbers look a little bit more complicated, some really cool patterns emerge and we can figure out some pretty awesome stuff. Okay? So using standard form a plus bi all the time can get really cumbersome, especially if we're finding powers of them and different things like that. So what we're going to do is we're going to write them in what we call trig form. And this actually makes operations, finding powers, finding roots, multiplying them, dividing them, and stuff like that, it actually makes it quite a bit easier. Okay? So we write a complex number in trig form by recognizing that every complex number can be located, okay? So located on this complex plane using the distance from the origin, or another way to call that would be the distance from 0, and an angle measured from standard position. So this one right here, we could actually find that point by measuring two things. I could measure how far it is from 0, and I could measure this right here. Kind of like we do with vectors, a magnitude and a direction angle, except for here we've got a modulus and a direction angle, okay? So the trig form of a complex number, a plus bi, would look like this. We've got a radius, or a modulus, okay, because that's what it looks like when we draw it on there. It would look like a radius. And then cosine of the direction angle plus I times sine of the direction angle. And I'm going to show you this in just a second. Where a is r times the cosine of theta, and b is r times the sine of theta, and we already know how to find the modulus, we know how to find the radius, it's the square root of a squared plus b squared, okay? And tangent of theta is equal to b minus a. Now, the tangent of theta might be equal to b minus, or b over a, but if we were to go backwards, if we wanted to say tangent, or theta equals tangent inverse of b over a, would that tell you exactly what the original direction angle was? No. What would it tell you? It would give you a reference angle. So remember, if you're going backwards and you're trying to find that, you'd have to be careful with that. Okay? So we've got the modulus, and that angle, we call that angle the argument. Okay? Now, off to the side here, I've got a little box that says this, and I'm not a huge fan of this, but if you did ever see this in a class or somebody mentioned this to you, there are times where this gets a little bit complicated to write over and over again. It's a little bit cumbersome. So sometimes we'll write things like this, r cis theta. And what that means is, this is the modulus, cosine of that angle plus I times the sine of that angle. So if you ever see anything r cis theta, okay, it's just shorthand for the exact same information, okay? So you're going to have problems where they say convert from standard form to trig form. So we've got this number right here. We want to convert from standard form to trig form. We need two things in order to do that. We need to know what r is, and we need to know what theta is. So let's think about when we graphed this. Didn't we already figure this out? This was radical 3, this was 1. What's r? R was 2. And if you look closely at that, can you figure out what the angle is? What's the angle? 1, radical 3, 2. The hypotenuse is twice as big as this side right here. What type of triangle is this? 30, 60, 90. This angle right here would be the big angle or the big angle or the small angle? It'd be the small one. It's going to be a 30. Just for the heck of it. Now we're in quadrant 1, so this is totally okay. Let's do tangent inverse. Grab your calculator. Tangent inverse of, notice that it's b over a. So we're going to do 1 over radical 3, and we're going to hope the calculator spits out 30 degrees, right? And what does it say? 30 degrees. Okay? So if we write this in trig form, we write down the modulus, parentheses, cosine of the direction angle, plus I times sine of the direction angle. So hopefully you see some similarities here. Notice the cosine has something to do with how far we go in the horizontal direction, the real direction. The sine has something to go with how far we go in the vertical direction, the imaginary direction. It's kind of like just working with a vector. And that's the scalar that sits out front. So we've successfully converted that. And think of it this way. We turn to an angle of 30 degrees. So turn to an angle of 30 degrees and go out 2 units. And that's where that point would be located. Okay, any questions? Okay, this one's just a little bit more difficult because this one isn't going to work out very nicely. -3 for the real part, -2 for the imaginary part. So we're going to go back 3 and down 2. So we're like this. We need to know what the radius is, and we need to know what the direction angle is. So the radius is pretty easy. That's going to be -3 squared plus -2 squared. So that's going to be radical 13, right? How do I find the direction angle? Okay, we're going to do a tangent inverse of, it's the b over the a, so -2 over -3. And what does your calculator tell you? What is it? 33.69 degrees. 33.69 degrees. Is there any way that this angle right here from standard position is 33.69? It's not. Remember, that gives you the reference angle. So what do I do to find the actual direction angle then? Add to 180. So I'm going to get 213. Is that right? 213.69. So in trig form, this is going to be radical 13 cosine 213.69 plus I times the sine of 213.69. And that right there, we've successfully changed that from standard form into trig form. Any questions there? Okay, couple quick things to note on the first page. Please note that there are a lot of angles that would be coterminal with any angle theta that we wanted to use. So there are a whole bunch of angles that I could use here. I could use the angle that we used, 213.69. I could figure out a negative angle that would work. I could go 213.69 and then add 360. We usually use the smallest positive angle we can. Smallest positive angle we can. Okay? All right, any questions? Okay, you can just watch up here. That right there is shorthand for this. I'm not a huge fan of it. Some people really like it. Okay, I like writing this out because then I can see, hey, there's the real part. There's my horizontal component. There's the imaginary part, and it actually shows that I'm adding these together like they are in standard form, because we do add the real part to the imaginary part, okay? But just keep note of that. If you want to practice with that a little bit, that's totally okay. Any questions? Okay, so here's the next type of problem you'll have. Convert from trig form to standard form. This is how long it is. That's the direction it goes. And all I need from this are radical 2 over 2 plus I radical 2 over 2, and then distribute the 10 through. So this is going to be, I'm going to cancel the 2 with the 10, so this is 5 radical 2 plus, what do I write? Remember the 10 and the 2 are going to cancel, so that's going to make a 5 again. So I'm going to write 5I radical 2, okay? Now, there are some people that do this. Is there anything wrong with this? There's not really anything wrong with this, as long as it's perfectly clear that the I is on the very end. Some people will get confused and they'll think the I might be underneath the square root. So by convention, we usually pull that I out in front of the radical. But it doesn't matter as long as it's clear, especially if you put a set of parentheses around that, that would be totally fine. This is a little bit more conventional though. Any questions? Any chance of doing this one without a calculator? No chance. So what we're going to do on this one is I'm going to do this. Okay, and remember that nice deep recall command on your calculator? I'm going to make sure I'm in degree mode, and then I'm going to type in 4.2 cosine 106. I get negative 1.5 or negative 1.157. And then plus, all I'm going to do is hit second enter. All I have to do is change this from a cosine to a sine, and I end up with 4.037. Any questions? Do I need anything else on here? Yeah, don't forget that I is sitting there for a reason. We're always representing a complex number. So we've gone from trig form to standard form, and up above, standard form to trig form. Which one's easier? Standard to trig or trig to standard? Trig to standard is a lot easier, okay? Now, I will tell you this. We're going to do several operations now, and I'm going to show you how we can multiply complex numbers in trig form, divide complex numbers in trig form, raise them to powers, find roots of numbers in trig form. And those are really complicated operations if we didn't have trig form. And there are some books that make you go back and forth from trig form to standard form and so forth. For this book, for the most part, they allow you to keep the answers in trig form, which is a huge advantage. Okay, and they also give you most of them in trig form. Okay, so let's take a look at this. Now, just like I said, with logarithms, it seems like we're making things really complicated. Okay, why on earth would we want to write a number in trig form? Okay, well, we're going to show you why. Okay, if I've got two numbers in trig form, so here's a complex number in trig form and there's a complex number in trig form. If I want to multiply the two of those, I can do it in trig form very easily. I take the two moduli, that's the plural of modulus, moduluses, I suppose. Okay, we multiply those together and we add the angles. Okay, so when you're multiplying complex numbers in trig form, we multiply the moduli and we add the angles. Well, let's fill this one out because this is the opposite. Dividing is the opposite of multiplying. So if you're dividing complex numbers, guess what we do with the moduli? Okay, well we go ahead and we divide those and we subtract the angles. Okay? So it seems kind of weird that it would work this way, but this is in fact the way it works, and we could actually prove these using the law of, the sum and difference identities for sine and cosine. Okay, and they go through a quick proof in the book, and if you wanted to see more, you could look it up on the internet or look in the appendix. I think they've got something in there. Okay, so if I'm going to multiply the two of these together, now remember, we multiplied these complex numbers together. We got this, simplified it to be that. If we're multiplying these complex numbers, because they're in trig form, here's all I have to do. Multiply these two guys together. That's a 6. What do I do with the angles? Add them together. So if I take 150 and 300, I get 450. Now, is there anything wrong with this? What's that?
Would it be 2i? Since you added 2i's?
Oh, no. We don't, so if you take a look here, we don't add another I. Okay, we're just adding or subtracting the angles. Everybody good with that? Is there anything wrong with the way this is written? It's not the smallest positive angle that's coterminal with 450. So let's subtract 360 and I get this. Subtract 360, I get 90 plus I sine 90. If I wanted to, this answer right here is equivalent to that answer right there. Now, they don't ask for it on this one. In fact, it says specifically leave it in trig form, which is a huge advantage. But if I wanted to, I could change this into standard form. Let's just do it for fun on this particular one. What is the cosine of 90? 0. So that would be 0 for the real part. And what's the sine of 90? 1. So this would be 1i times 6. So this would be plus 6i. And there it is. So the answer would just be 6i. Relatively simple compared to the multiplication that we had before. Okay? Any questions there? Okay. What's my new modulus if I'm dividing the two of these? 5, piece of cake. Cosine of, what do I do with these angles? Subtract them. Bit of a pain in the butt because it's in radians. So I'm going to need twelfths here. This is going to be 3 pi twelfths. This is going to be 2 pi twelfths. And whatever one is on the bottom, whichever one I'm dividing by, that's the one I subtract. So I'm going to take pi fourths, subtract pi sixths. 3 pi twelfths minus 2 pi twelfths, what do I get? Pi twelfths. There's the answer. It says leave it in trig form. We're done right there. Okay? Okay, remember, if you have something like this, and you have to divide those numbers, you have to multiply by the conjugate. You have to multiply the bottom out, you're going to have a difference of squares, you're going to have a real number on the bottom. You're going to have to multiply the top out, collect like terms, and then write the final answer. Look how fast this is. Okay? Any questions? Sure? Good. We're in great shape then. Okay, I'm hoping to get at least to the bottom of this page right here. So this is a problem very similar to one on your assignment. It says, given that Z1 is this complex number in trig form, and Z2 is this complex number in trig form, find Z1 times Z2. So if we're multiplying, what do we do with the moduli? Multiply them. So I'm going to get 16. What do we do with the angles? Add them together. So I've got 2 pi thirds plus 11 pi 6. Let's see what I've got here. Let's make this 6. So that's going to be 4 pi 6. So that's going to be 17 pi 6. Correct?
15 pi.
Oh, 15 pi 6. Thank you. 15 pi 6. 15 pi 6? Okay. Think about that for just a second. What's wrong with writing down 15 pi 6? Okay, it's bigger than 2 pi, isn't it? Okay, so let's subtract off 12 pi 6, and I end up with 3 pi 6, which is, lo and behold, it's pi halves. Lo and behold, that's pi halves. So this is pi halves plus I sine pi halves. Okay, there's the answer, in trig form. Then it says, confirm your answer by converting the number to standard form and then multiplying. Okay, so we're going to do two things. Okay, I want to write down what number this is in standard form. I want to know what number I'm looking for in standard form. Cosine of pi halves? 0. Sine of pi halves? 1. So the answer to this is 69, isn't it? Does that make sense? Any questions there? Okay, so let's take this one and let's convert this into, so I'm going to change colors. Let's convert this into standard form and see how much work we'd have to do if we were going to do this the other way. So 2 pi thirds, cosine of 2 pi thirds, isn't that negative 1/2? Sine of 2 pi thirds, radical 3 over 2i. And then if I multiply by 2, so if I've got the 2 out front, isn't z1 going to be negative 1 plus radical 3i? Isn't that what the first number is in standard form? Okay, let's do this one. Have an 8 out front. 11 pi 6. 11 pi 6, and I need a cosine for that. Cosine of 11 pi 6. We're in quadrant 4. It's that small one. It's going to be radical 3 over 2, right? Plus, I need the sine of 11 pi 6, 30-degree angle. That's going to be negative 1/2, so I'm going to write minus 1/2 I. So if I distribute through, the 2 and that's going to cancel. So Z2 is going to be 4 radical 3, and then minus 4i. Okay, now look how easy it was to multiply these together in trig form. Let's do this. Negative 1 plus 3 radical 3i, 4 radical 3 minus 4i. So let's multiply these together. That's going to be minus 4 radical 3. This one's going to be plus 4i. Multiplying these together, I'm going to get a 4, and a radical 3 times a radical 3 is a 3, and then an I, right? And then if I multiply these together, I get minus 4 radical 3 I squared, right? What does this count as? A positive. Whoops. Those two go away. So I end up with 4i plus 12i, which is 16i. Which one's easier? By far. By far. Okay? Even if you were given these numbers to begin with, this is a really quick process to figure out. Okay? So everybody see that it does indeed work. So we know how to convert from trig to standard, standard to trig. We know how to multiply them in trig form, and we know how to divide them in trig form. Okay? And now we're going to do something kind of interesting. Okay? We're going to take this number right here, and we're going to figure out what happens when we square it. So I'd be multiplying it by itself, right? What do I do with these guys? Multiply them together. So that's going to be 2 squared, or 4. What do I do with the angles? Add them together. So what do I get? I get pi halves. I'm going to write it as 2 pi fourths plus I sine 2 pi fourths. Because I had 2 of those that I added together. Is that right? Okay. What if I cube it? Let me write another one. So I'd have to multiply all of these together. What do I do with the moduli? Multiply them all together, so it'd be 2 times 2 times 2, so that's going to be 2 to the third. Cosine of, I'd add all of those together, so what would I get? 3 pi fourths. And what would happen if I threw another one on there? So I did another 2 cosine pi fourths plus I sine pi fourths. 2 to the fourth. Cosine of pi, or I'm going to write it 4 pi fourths if that's okay, so we can kind of spot the pattern. And then I sine 4 pi fourths. So what if I said raise it to the n? Write down a formula for raising that number to the nth. If we had written pi halves here and pi here, it's a little harder to spot what the formula would be. This is pretty easy. What do I write here? Okay, so I write 2 to the n, and then cosine of n pi fourths plus I sine n pi fourths. So when we raise it to a power, think about what we do. We're going to raise the radius or the modulus to that power, but we're going to take the angle and we're just going to multiply it by that power. Make sense? Okay. So this is a theorem that was actually come up with by a French guy named de Moivre. Okay, so here's how his name is spelled. Okay, so don't say de Moivre. Okay, it's pronounced de Moivre's. Okay, act like you're from France or something. So that's called de Moivre's theorem. Okay, de Moivre's theorem, and it looks like this. If we know what a complex number is in trig form and we want to raise that to a power, here's what we do. We take the radius, the modulus, we raise it to the nth. And then we take the angle, whatever theta was, and we multiply it by n. So we're going to do one problem here, and then I'm going to leave you to do that one right there and see if you can figure that one out tonight. You can get started on the homework. You can do a lot of it. If we write this in trig form, it's got to be in trig form to begin with. Does anybody remember what the radius was? It was 2. Okay. And what was the direction angle? It was 30 degrees, wasn't it? Okay. Plus I sine 30 degrees. Now, if I take this and I raise it to the 8th, I'm going to end up with 2 to the 8th. What's 2 to the 8th? 256. Okay? What am I going to do with the angle? Times it by 8, and what do I get? I get 240. So cosine 240 plus I sine 240. Okay? And there it is. Okay? You figure out that one, and then what we're going to do tomorrow is we're going to cover this idea that comes up next. So we'll easily be able to finish that. Get started, maybe do a couple problems on 6.5. Please make sure you're done with 6.4. We'll turn that in at the beginning of class.